Hello everyone and welcome back to the channel. In system design, ensuring atomicity, the all or nothing property of transactions, is straightforward with a single database. But what happens when a single transactions need to update data across multiple independent databases or services? How do you guarantee that either all updates succeed or fails, even if things go wrong? This is a complex world of distributed transactions. And a classic solution is the two-phase commit or 2PC. So two-phase commit protocol is important for that. And in interviews, understanding 2PC demonstrates your grasp of crucial consistency challenges. So today we are diving into how 2PC work and its vital role. Okay, first, as always, we understand the problem. The core problem 2PC address is achieving atomic commitment across multiple independent resources. So you can imagine an e-commerce order. You need to first dip the customer's account in your payment service data. Number two, update inventory in your inventory service data. Number three, create an order record in your order service database. If the payment succeeds, but inventory update fails, you have an inconsistent state. All three operations must either all commit successfully or all roll back. In a microservices or distributed environment, these databases are separate, making this a significant challenge. 2PC provides a way to coordinate this global all or nothing decision. Okay, so what is 2PC commit? A two-phase commit is a distributed algorithm that allows a group of participants, databases, or services to collectively agree to commit or abort a transaction, orchestrated by a central entity called the Transactions Coordinator or Global Transactions Manager. Its goal is to maintain asset properties, atomicity, consistency, isolation, durability across these distributed resources. It ensures that either all participants commit the changes or none of them do. Okay, so let's try to understand how it works. So we have two phases. Let's talk about phase one. Phase one, the coordinator will send a prepare. The transaction coordinator here will basically will warm everything up. So it will the transaction coordinator, which could be application server, a dedicated service, or maybe a database itself acting as a coordinator, will send a prepare message to all participating databases and services involved in the transaction. Here it sends like a request, and they send OK. After that, the participants will respond with this OK. You can see this OK here. So each participant receives the prepare message. They then perform all necessary operations locally, like check if they can, check if they can indeed commit. Maybe they lock the resource involved in the transaction to prevent other transactions from interfering. Also, they log their changes to ensure durability in case of failure. If a participant is ready to commit, it responds, yes, I can commit to the coordinator. If it cannot commit for any reason, it sends, no, I cannot commit. Next, we have phase two, which is the commit phase. The coordinator waits for response from all participants. If all participants respond yes, the coordinator decides to commit the transaction. It then sends commit message to all participants. If even one participant responds with no, or if the coordinator times out waiting for a response, the coordinator decides to roll back the transaction. It then sends a rollback message to all participants. Lastly, we have participating execute decisions. Upon receiving a commit message, participants finalize their changes and release their locks. Upon receiving a rollback message, participants undo their changes and release their locks. once a participant has voted yes in phase 1, it must commit or roll back based on the coordinator final decision. Okay, so let's try to understand the advantages and disadvantages. The advantage, I guess it's quite clear. We have a strong atomicity and strong consistency. Its primary advantages is ensuring strict all or nothing atomicity across multiple resources. Also, I would say quite simple because the two-phase structure is relatively easy to understand, I would say. The cons of it, first we have blocking. This is the biggest flaw, I would say. Participants hold locks on a resource for the entire duration of the transaction, including during the coordinator's decision-making process. If the coordinator fails during phase 2, participants can be left to hold locks indefinitely for a long time, leading to resource contention and reduced availability until manual intervention or a complex recovery process occur or happens to save this problem. Number 2, I guess we have a single point of failure because the transaction coordinator is a central point of failure. If it crashes at a critical moment, it can lead to huge problem and hung transactions or inconsistencies. Number 3, performance involves significant network overhead and higher latency due to blocking and locking contentions. And also, I would say it's not ideal for microservices. Like, it creates tight coupling between services, which goes against the independent nature of microservices. Okay, so how to discuss that in system design interviews? So I would say in system design interview, you can discuss 2PC when the problem explicitly demands a strong, immediate asset guarantees across multiple tightly controlled resources where you can tolerate higher latency or temporary unavailability. For example, in a traditional enterprise system or within a tightly coupled system where transactions span a few databases. It's often constrained with the Saga pattern for microservices, which trades immediate consistency for scalability and availability. Generally, for cloud-native microservices, 2PC across independent services is often advised against due to its blocking nature. However, knowing its mechanism and drawbacks is essential for a complete system designer toolkit. So that's it for this video, and see you in the future.